morning students, welcome to Engineers Career Group. I am Deepak Pal and I am a faculty of mechanical engineering here, and I am going to teach you subject theory of machine. So today's topic is inversions of kinematic chain. So first question is, what is kinematic chain? So I will take an example of engine. So this is a crank, this will be your connecting rod, piston and cylinder. So this is a simple example of a machine. So you can see this energy of here produced by the gas is transferred to piston, then piston to connecting rod, then connecting rod to crank, and then crank to outside the flywheel. So that energy we can utilize for driving the vehicle. So you can see here the energy is transferred from piston to connecting rod and connecting rod to crank. So these parts, which is cylinder, piston, connecting rod and crank, these are work as members, and these members are known as elements or kinematic link. So first thing is link. So parts which transfers motion and forces is known as kinematic link. And the second thing is, what is linkage or what is chain? So if you are going to if you are connecting these links, like say 1, 2, 3, 4, here are 4 linkages and you are connecting this in this way, 1 with 2, 2 with 3, 3 with 4. So you are obtaining a linkage which is known as chain. So this chain can be 3 types. So first type is chains. So first is kinematic chain, second is non-kinematic chain, and third is redundant chain, or sometimes called locked chain. So a kinematic chain, there is a motion is possible and the motion between links is definite. So in kinematic chain, motion between the links is constrained and predictable. So motion between the links is constrained and predictable. The motion between the links is constrained and predictable. Now the second is non-kinematic chain. In non-kinematic chain, the motion between the links is not constrained and neither predictable. And the third is redundant chain. So between the motion between the chains is not possible. So how to predict which is a kinematic chain, which is a non-kinematic chain, and which is a redundant chain? for that we have an equation J plus h by 2 is equal to 3 by 2 n minus 2. So here J is number of binary joints, h is number of higher joints, n is number of links, and if LHS and this is RHS, so for kinematic chain LHS should be equal to RHS. For non-kinematic chain LHS is less than RHS, and for redundant chain LHS is more than RHS. So by using this equation we can find which chain is a kinematic chain or non-kinematic chain or redundant chain. Then now we will start with mobility of mechanism. Now, as you already know, a body has a degree of freedom 6. What are the degree of freedoms? So, if we have a ball in space, then this ball can go along x direction plus or minus, it can go along y plus and minus, along z plus or minus, and these are three transverse motion. Then this ball can revolve around x-axis, y-axis and z-axis also. So there are three rotational motion. So total degree of freedom is 6. So now for mobility of mechanism, so we are generally using planar mechanism. So total degree of freedom for a mechanism is 3 L minus 1 minus 2 P1 minus P2. So as we know, for a planar mechanism the maximum number of degree of freedom can be 3. So as for mechanism one link should be fixed. So the number of maximum degree of freedom can be 3 into L minus 1. Now if there is a link with single degree of freedom, then it will put 2 restraints on the mechanism. So minus 2 in P1, and if there is a link with only 2 degree of freedom, then it will put 1 restraint. So minus 1 P2. So this equation we can modify and we can write this equation we can write as Kurzweil equation here. L is number of links, J is number of lower pair and H is number of higher pair. From this equation we can find out degree of freedom for any mechanism. Now we will start with inversions and we will start with the 4-bar kinematic chain. So as I already told you that a kinematic chain the motion between the links is constrained and predictable. So, for 4-bar kinematic chain, there will be 4 links. One link, second link, third link, and fourth link. And motion between these links are constrained and predictable. For the mechanism, so for any mechanism, one link should be fixed. So, second thing is inversion. What is inversion? Inversion nothing with the mechanism which are find out or which we are getting by fixing different links of a mechanism at different times. So, again the inversion is the mechanism obtained by fixing different links at different time. So, first in the 4-bar mechanism there will be a sorry. So, in any mechanism there will be a shortest link, there will be a longest link, and there will be a other 2 links. So, here I am taking this as a smallest link, this one as a longest link, and these are 2 other links. So, 4-bar mechanism, a Grossop's gives a law, and according to that law, for continuous motion of at least one link, so smallest and longest should be less than and equal to the rest of 2 links. So, according to the Grossop's law, for continuous motion of at least one link, the sum of smallest link and longest link should be less than or equal to the sum of rest of 2 links. So, this is the first condition which we have to apply on this 4-bar kinematic chain. So, here you can see the motion should be continuous motion of at least one link. So, continuous motion of at least one link, this equation should be satisfied. So, we are now fixing different, now we are going to fix different links at different times, and we are going to obtain different mechanism. So, mechanism if we fix a link of a kinematic chain, then a mechanism is obtained. So, we will start with 4-bar kinematic mechanism. Now, smallest, longest, P and Q. So we will start with case 1. If smallest plus longest is less than P plus Q. So this is known as class 1 linkage. And in this case, if we fix adjacent to smallest is fixed, then we will obtain crank rocker mechanism. So fix smallest, this is the smallest link and this is the adjacent link. So we are fixing any one of link. Say we are fixing this link. So this S link will make a complete rotation and this Q will oscillate. So this type of mechanism is known as crank rocker mechanism. So this link is known as crank. The link which oscillate is known as lever or rocker, and this will be the coupler or connecting rod. So if we fix the adjacent to smallest, then we will obtain crank rocker mechanism. The application of crank rocker mechanism is in beam engine. So then the second is, if we fix second case, if we fix opposite to smallest, then let's fix the opposite to the smallest. This is the smallest, this is the longest, P, Q. So fixing opposite to smallest. So in this case, we will obtain double rocker mechanism. So in double rocker mechanism, both the link will be oscillating and the smallest link will make complete rotation. Then if we fix the smallest link, the third possibility, if we fix smallest link, then we will obtain double crank mechanism. So smallest is fixed, smallest, longest, P, Q. So if smallest is fixed, then this link and this link, the longest link and the link Q can rotate a full circle So we will obtain a double crank or drag crank mechanism. So these are all three possible mechanisms which we can obtain from a 4-bar mechanism. So this is only for the case if smallest plus longest is less than P plus Q, and it is known as class 1 linkage. Now if there may be a second possibility, that case 2, if smallest plus longest is more than P plus Q, then it is known as class 2 linkage. And in this type we already know what is the Globulars rule, that if the sum of smallest and longest is less than or equal to sum of other two links, there will be a continuous motion of at least one link. So this rule is not followed. So here you will always obtain a double rocker mechanism. Now there may be a third possibility, case 3, if smallest plus longest is equal to P plus Q and there are two pairs of equivalent length of links. So the third case, if smallest plus longest is equal to P plus Q sorry, and there are two pairs of equal length of the links, that means there will be smallest, longest and longest. So here again there are two possibilities. One possibility is smallest is fixed with longest, and second is smallest is fixed with smallest and longest is fixed with longest. So smallest, longest, smallest, longest. The first one is known as linkage. So first one is known as parallelogram linkage. If you fix any one of the link, maybe longest or smallest, you will obtain a parallelogram linkage which is used in locomotives. So you have seen, so there is a rod in wheels of locomotive and it is used for transferring power from one wheel to other wheels. So coupling rods of locomotives. Is used by the parallelogram linkage. Second is deltoid linkage. So if you fix smallest and longest together, then you will obtain deltoid linkage. So this case where smallest plus longest is equal to P plus Q and we have two pairs of equal length, then this is known as class 3 linkage. Now how to use these inversions in gate. So problem will be like, Like every year we see there is a problem like this one, 8, 5, 6, 7. So in this problem they are giving that the link with length of 7 is fixed. Which type of mechanism this is? So to find out which type of mechanism this is, the first step is check which is smallest. Smallest link is 5 and the longest link is 8 and P is 6 and Q is 7. You can take Q as 6 or P as 7 as your wish. So sum of smallest plus longest and P plus Q, we can check 5 plus 8 and P plus Q 6 plus 7. So you can see 5 plus 8 and 6 plus 7 both are is, so 5 plus 8 and 6 plus 7 is equal to. So this is a class 1 linkage and opposite to smallest is fixed. So this will be always a double rocker mechanism. So how I find out? First thing is this is a class 1 linkage. Why it's not class 3rd? As there is no equal pair of links, like the links length, the sum of links smallest and longest is equal to P plus Q, but still there is no equal length pairs. So this will be only in class 1 linkage. Second thing, the step 2 is which one is fixed link. So here you can see the link opposite to smallest. So this one is your smallest link. So opposite to smallest is fixed. So we already know that if smallest the link opposite to smallest is fixed, then you will always get a double rocker mechanism. So in this way we can solve the problem which we will face in gate examination. We will take another example. Take 12, 7, 5, 8. So which one is smallest here? This one. And the longest one? This one. Smallest, longest. Now the question may be that which link should be fixed to obtain a crank rocker mechanism. So we will first see which kind of linkage this is. So smallest plus longest, P and Q. So smallest is 5th, longest is 12, P is 7, Q is 8. So here you can see 17 and here you can see 15. So 70 is more than 15. So the law is not satisfied. So it will be always a double rocker mechanism. So if the question is which link should be obtained to fix the to get the crank rocker mechanism, so answer will be no, we cannot fix any link as it is always a double rocker mechanism. So the 4-1 mechanism is completed. Now we will move to single slider crank mechanism. In single slider crank mechanism, we have 4 links with 3 turning pair and one sliding pair. So in 4-hour mechanism, if we replace one turning pair with one sliding pair, we will obtain single slider crank mechanism. So I am just draw a schematic diagram of single slider crank mechanism. So here you can see this one is a crank which makes a complete rotation. Then this one is slider which slides inside the cylinder. This is cylinder. And this is coupler, or sometimes say connecting rod. So the crank is the link which makes complete rotation, the coupler which transfers energy from crank to slider or slider to crank, and the slider is the link which reciprocates inside the cylinder, and cylinder is the slotted arm in which slider reciprocates. So now the first inversion we get when we fix the cylinder. So fix the cylinder. By this we will get IC engine, and the second is reciprocating pump. So both the thing is same, just the input and output source is different. So this is slider and crank. If slider is input and crank is output, it is IC engine, and if slider is output and crank is input, then it is reciprocating pump. So we know in IC engine the gas pressure moves piston, so that is a input, and we obtain energy on the crank, that is a output. But in reciprocating pump it is different. In the slider we are obtaining the output, we are getting the output, and on the crank we are putting the input, we are giving the input. So this is the first inversion. In the second inversion, we will fix the crank. By fixing the crank, we will obtain two mechanisms. First is Whitworth quick return mechanism, and second is rotary engine, or sometimes called gnome engine. So if we fix the crank, we will obtain Whitworth quick return mechanism and rotary engine or gnome engine. So the third inversion, which is a very important one, it is obtained if we fix the coupler. So if we fix the coupler, we will obtain two mechanism. First is crank and slotted lever. Quick return mechanism, and the second one is oscillating cylinder. Oscillating cylinder mechanism. So this one is very important for the point of view of gate. So we will explain this later in next video. So this is the third inversions. When coupler is fixed, we will get a quick return mechanism and a oscillator cylinder mechanism. Now if we fix fourth link, that is a slider. So now slider is fixed. So if we fix the slider, we will obtain pendulum pump or hand pump mechanism. So these are the all possible inversions or mechanism which we are obtaining from single slider crank mechanism. We will discuss with crank and slotted lever mechanism, which is very important, and almost every year there is a question in gate from this topic, crank and slotted lever mechanism. So crank and slotted lever mechanism. So as we know, in shaper machine and planar machine sorry, crank and slotted lever mechanism. In shaper machine, during the cutting, the speed of tool is slow as it experiences cutting force. So during cutting, speed of tool is low, but in non-cutting stroke we required a higher velocity of tool as we can reduce the machining time. So during return stroke, speed of tool should be high. So in one stroke the speed is low, that is cutting stroke, and in the return stroke the velocity should be high. So these things we can obtain by a quick return mechanism. So crank and slotted lever mechanism works as a quick return mechanism. So it is used mainly in shaper mechanism. So in shaper machine this quick return mechanism is used. Now how it is looks? Now the coupler is fixed. This is your crank, this is your slider, and this is the slotted lever. So say this is R, this is C, and this length is L. So R is length of crank and L is length of slotted lever. So first thing we are going to obtain is stroke length. So this will be like this one, this will move like this one, and then here it will go like this, and this will be a maximum position when this angle is 90 degree. So down I am putting the name of points O, A, B, C, D and C dash. So now when OB is perpendicular to BA or AC, then this link will be in extreme positions. So our stroke length will be C to C. It is CC dash, and it is this CC dash is twice of CD. Twice of CD. Now to find out this stroke length, let this angle here this angle is beta and this angle is alpha. So this angle will be beta by 2. This is already 90. So this angle will be also beta by 2, as this is beta by 2, this is 90. So this will be 90 minus beta by 2, this will be 90, and in the same triangle this is 90, this is 90 minus beta by 2, so it will be beta by 2. So first we will take triangle OBA. This triangle cos beta by 2 is equal to, what will be the cos beta by 2? R upon C. Now in this triangle CDA, cos beta by 2 will be L and CD. So CD upon L. Now both the value of cos beta by 2 is equal. So we can write R upon C is equal to CD upon L. So from here CD is equal to R into L upon C. Now stroke length is CC dash, which is twice of CD. So CC dash or stroke length will be twice of R into L upon C. So this is the formula which is very important to find out stroke length. Now the second thing, which is maximum velocity. So at the ends, when the oscillating link will be moving, here at the ends at the ends the velocity of oscillating link is 0, and when it will be passing through the center the velocity will be maximum. So we are going to find maximum velocities. So we are taking case 1 when piston is in cutting stroke. So this is R and crank and oscillating link are collinear. This is C, point A, O, B, C. So this is our fixed link. So let OB is rotating with omega angular velocity, so, and AC is rotating with omega dash angular velocity. So velocity at point V, at point V of slider will be BV is equal to, so velocity will be omega, this is omega and this is omega dash, so omega into R we already know. Now velocity of link AC at point B, let's say BV is equal to omega dash into C plus R, this velocity BV. So omega dash into C plus R. Now at this point both the velocity are equal, that is the velocity of slider and velocity of this point on link AC. So BV and VV this will be equal to, so omega dash into C plus R will be equal to omega into R, and from here we can get omega dash is equal to omega into R upon C plus R. Now if we have to find the velocity of point C, so velocity of point C will be omega dash into this distance. What is this distance? L. So omega into L. And what is omega dash? Omega R into L upon C plus R. So this is your formula. I am writing here again. So this is the velocity, maximum velocity during cutting is equal to omega R L upon C plus R. Similarly, we can get maximum cutting velocity in return, which is omega into R C minus R. And the quick return ratio QRR or simply QRR is the time taken in cutting stroke divided by time in return stroke, that is given by alpha upon beta, or we can write 360 minus beta upon beta. So by using this 1, 2, 3, and the first formula, which is stroke length, is equal to 2r into L upon C. So by using these 1, 2, 3 and 4, by using these 4 formula, we can solve any problem which is related to crank and slotted lever mechanism. Now we will talk about Coriolis acceleration component, which is acting in single slider crank mechanism. So wherever there is a slider moving on the link and link is rotating, there will be a Coriolis acceleration component present. So now we will take a simple example of disc rotating about the center O, and it is moving with angular velocity omega and angular acceleration alpha. So if we take a point A and the distance between this point from O is r, then tangential acceleration, we are saying at will be alpha into the distance r, and the centripetal acceleration or radial acceleration will be omega square into r, or we can write v square upon r. So now we will take a link Now this is a link which is rotating with angular velocity omega and angular acceleration alpha, and we have a slider on this link which is moving with velocity v and linear acceleration f on the link. So link is rotating and also the slider is moving with velocity v and linear acceleration f. So now after some time, say dt, it will be change its position. The slider will change its position. So say after dt time, it will make an angle d theta, and slider will move from here to somewhere here. So say this is the new position of slider. So you can see, so from here to here, this slider is moved because of acceleration f from here to here, and from here to here, if we say if this acceleration, linear acceleration is not present, then slider's position will be this, and if angular acceleration and angular velocity is not present, then slider position will be this. So the combined effect will be shown here. So the slider is reached from here to this position. So now you can see this is because of omega and alpha, and this is because of f and v. So this is the combined effect. Now if you see this omega, the effect due to the tangential acceleration here, this is up to here, this extra acceleration component is called Coriolis acceleration component. So Coriolis acceleration component value is given by 2v into omega. So this value should be added into the tangential acceleration. So now tangential acceleration will be alpha into r plus minus 2 v into omega. This is the total tangential acceleration. Total tangential acceleration. Now similarly, the total radial acceleration now this because of this rotation there will be a sorry radial acceleration which is omega square into r, and due to the movement of slider there is also a acceleration. So total radial acceleration will be sum of radial acceleration, centripetal acceleration, omega square r, and the sum of this one f plus minus linear acceleration of slider. So total radial acceleration will be given by this one. Now the direction of f will be positive if the slider is moving downwards, as centripetal acceleration the direction of centripetal acceleration is always downwards, and if f is downwards then this equation will be positive. So f will be positive if it's moving or it's accelerating towards to center of rotation of link. Otherwise it will be negative. Now the important thing, how you will going to give the direction of Coriolis acceleration component. So I am drawing all four possible combination. I am drawing all four possible combinations of slider and link motion. Say this is moving here and the link or slider is moving upward. In this case, to find the direction of Coriolis acceleration component, just took the velocity vector of slider. This is the velocity vector of slider and turn it in the direction of angular acceleration of link. Now if we turn this velocity vector in the direction of link, we will get this direction. So if you turn this velocity vector in direction of link by 90 degree, you will get the direction of Coriolis acceleration component. So this is the direction of Coriolis acceleration component. So this is the direction of Coriolis acceleration component. In first case, if the link is rotating in anti-clockwise direction and slider is moving upward direction, now rotate it by from here in 90 degree in the direction of link by 90 degree, then you will get this direction. So this is the direction for the second case, Coriolis acceleration component direction. Now if omega is rotating in clockwise direction and slider is moving downwards, then rotate it in the direction of link, rotate by 90 degree, you will get the acceleration component direction here. And in the last case, if it is rotating anti-clockwise and moving downwards, then again if you rotate it by 90 degree, you will get the direction here, direction. So this is the odd possible case to find out Coriolis acceleration component. Now we will take some examples. The general numericals which we face in gate examinations are like, I am taking first example, example 1. The first example, we are taking the given thing is the radius of crank OA. The radius of crank OA is given, say 5 centimeter, and OB is given, say 10 centimeter. Okay. So, and what will be the quick return ratio? So question will be like that, this OA is 5 centimeter, OB is 10 centimeter, and what will be the quick return ratio? So I am just mentioning the name or dimensions, 5 and 10 centimeter. So for that we know already what is the formula to find out QRR, that is alpha upon beta is equal to 360 degree minus beta upon beta. Now we need this angle beta. If somehow we can find out this angle beta, then the problem will be solved. This is your beta by 2. So if we are able to find out this beta by 2, then we can get beta and we can find out QRR. So beta by 2 will be, so let's say this is a 90 degree, this is 5, this is 10. So cos beta by 2 will be 5 upon 10, which is 1 by 2, and cos beta by 2 is 1 by 2 when it is cos 60. So beta by 2 will be 60, that means beta will be 120 degree. So QRR will be 360 minus 120 divided by 120, that is comes about 2. So answer will be 2. This is first kind of problem which you will face in GATE examination. Now take second problem. The second problem which we will face, stroke length is given, (20 centimeter). First, then your length of oscillating link is 20 centimeter. Find QRR. For this kind of question, we can say, we know stroke length is given by omega into R So stroke length is given by 2 into R into L upon C. So we know that what is the stroke length? 20, 2, R, and what is length? Length of oscillating link is 20 centimeter, that is 20 divided by C. So 20 cancel, so C is equal to 2R. So now again it will become the same problem. This is R, this is C, and we know C is equal to 2R. So if C is 2R, then cos beta by 2 will be R upon C or R upon 2R 1 by 2. So beta by 2 again will be 60 degree and beta will be 120 degree, and QRR will be 2. Again we will get the same result 2. So this is the second kind of problem which we face in gate examination. Then third one is given that the ratio of maximum velocities are 3. So find QRR. What will be the quick return ratio? So we already know that what is Vmax return omega R L divided by C minus R. So return is maximum velocity, and similarly Vmax cutting omega R L C plus R. So the ratio of maximum velocities R will be Vmax R upon Vmax C will be C plus R upon C minus R, and it is given as 3. So this is value is already given. So from here we can derive C plus R is equal to 3C minus 3R, or we can write 2C is equal to 4R, or C is equal to 2R. So from here again the problem becomes same. Beta by 2 will be 60 degree, beta will be 120 degree, and QRR will be 2. So this is the third kind of problem which we face related to the topic crank and slotted lever mechanism, and this is the all possible 3 cases which we can face in gate examination. Now we will take fourth problem related to cranks and slotted lever mechanism. Now take the fourth problem. Say given a link is rotating with 2 radian per second constant angular velocity and a slider is moving away from center of rotation of link over the link with a constant velocity of 2 meter per second. Find Coriolis acceleration component and its direction. So this can be the question which we face in gate examination. So how we can solve this problem? So we know what is given. A link is rotating with 2 radian per second. Now this is the point, constant angular velocity. And second thing is, what is a slider is moving away from center. So just make a diagram. So take a link, say OA, and it is rotating about O point by omega is equal to 2 radian per second. Okay, now the velocity is constant, so alpha will be 0. So angular acceleration is 0. Then second thing is, a slider is moving away from center of rotation of link. So there is a slider which is moving away from center of rotation, over the link with a constant velocity. So with a constant velocity, so here also velocity v is constant and the value is 2 meter per second. So v is equal to 2 meter per second, and it is as a constant velocity, so f will be 0. So find the Coriolis acceleration component and its direction. So Coriolis acceleration component will be 2v omega. So 2 into v, what is v? 2, and omega 2. So the value will be 8 meter per second square. But the direction, which is very important. Now we can see the velocity is, the slider is moving upward and link is rotating in clockwise direction. So just rotate the velocity vector of slider by 90 degree in direction of link rotation. So I am moving this velocity vector in 90 degree in the direction of link rotation. So this is your velocity vector and I am rotating it in the direction omega by 90 degree. So this will be the direction. So this is the direction of your v omega, Coriolis acceleration component. So this is the second type of problem, this is the fourth type of problem which will face in GATE examination. We'll take one more example. Fifth example. So say there is a link which is rotating out point O and it is rotating by omega, say 5 radian per second, and alpha is 0 and the slider is moving downwards with velocity say 10 meter per second and the acceleration is 0. Find Coriolis acceleration component find Coriolis acceleration component and the direction of Coriolis acceleration component. So the Coriolis acceleration component we can find out like this: 2v into omega, that is 2 into 10 into 5, 100 meter per second square. Now the direction, now this is the velocity vector. Now the direction of link, rotate this velocity vector v into the direction of link. So if I try to rotate, now try to rotate clockwise. So clockwise I am rotating, so it will be like this, 90 degree. So this is the direction of 2v omega. So this is the all possible question which can come in gate examination. So I hope I have covered almost every area of the questions for the crank and rotative mechanism. So the first topic, inversion of mechanics, is completed. Thank you. We will connect in next lectures.
Subscribe to us now.